So I just wanted to do a little update here. Last year I didn't teach this, but it's something very important and you're going to learn it anyways, so you might as well learn it now while we're talking about the things that it's relevant to. So when we talked about optimization, or in particular when we looked at the consumer's problem, which is a constrained optimization problem, where optimizing or maximizing utility subject to a constraint. So it's a constrained maximization problem. There we go. I showed you kind of a simple heuristic way of solving it, right? We looked at it intuitively and we derived the conditions for optimality intuitively. So now I'm going to show you another way of deriving these conditions, and it's kind of a foolproof method, okay? If you set up this Lagrangian, okay, this method for solving constrained maximization problems, if you set it up appropriately or you set it up correctly, it will always give you the correct answer. Okay, and so in that sense, it's a good thing to know, and so I'm going to show you now how it works. I'm going to show you what the Lagrangian is, and I'm going to show you that in the end, it gives us the same optimality conditions for the problem that we've looked at. Okay, so I'll show you that it's the same thing, gives you the same answers, but it's a different way of arriving at it. And like I said, it's like a foolproof method, kind of. So as I mentioned, it's called the Lagrangian or Lagrangian, depending on how true to the French you want to be. And it's named after this guy here, Joseph Louis Lagrange, okay, who was a mathematician and a physicist and, general, back in the 1700s, scientists did everything. So, a man about town doing science. And like I said, it's just a method of constrained optimization. Okay, so let's think about what it is here. So imagine our same consumer's problem that we saw before. Okay, so the consumer wanted to maximize its utility, which is a function of both consumption and leisure. And how's it going to do that? By choosing consumption and leisure. Okay, those are the choice variables, C and L. And it's a constrained optimization problem because it's subject to a budget constraint. And we said that that budget constraint was just consumption is equal to, here we go, this is wage income plus profits minus taxes. Okay, so same problem we saw already. Note that you can rewrite this by bringing the consumption term to the right-hand side as follows. It would just be 0 is equal to, again, wage income plus profits minus taxes, and now minus C. So that's the same equation. I've just written it in a different way. So now another way to solve this maximization problem is to form the Lagrangian. So the Lagrangian is just a specific function, okay, and we denote it with this kind of fancy L. If you're famous enough in science and math, you get a letter devoted to you. So here's the Lagrangian L. And what's the Lagrangian? It's going to be equal to the function we want to maximize, so in our case, the utility function, plus lambda, which we call the Lagrange multiplier, multiplied by the constraint written in the way where, in this case, consumption was on the right-hand side. Okay, so when I say multiplied by the constraint, I mean multiplied by just this right-hand side when we set the constraint equal to 0. Okay, so let me write these. So the Lagrangian, again, is equal to, this is called the maximand, the thing we want to maximize. This lambda is called the Lagrange multiplier. And this is the constraint set equal to 0. Okay, so that's step 1 for the Lagrangian. We form this kind of special looking function here. And I'm going to copy it now and bring it to the next slide. Here we go. Good. So the next step is now to take the first order conditions. The first order conditions are just the derivative of this Lagrange function, the Lagrangian, with respect to two things. One is with respect to the variables that we are choosing, my choice variables. Okay, so remember, to maximize utility, I'm choosing consumption and leisure. So those are my choice variables. So in this case, I'm going to take the derivative of the Lagrangian with respect to both C and L. And I'm also going to take it with respect to lambda. And I'm going to set each of those equal to 0. Okay, so my optimality conditions, when I'm using the Lagrangian, become the following. Okay, so one will be the derivative of the Lagrange function with respect to consumption is equal to 0. Okay, because consumption is one of our choice variables. The next will be the derivative of the Lagrangian with respect to leisure is equal to 0. And to make room for my head, I better do this slightly to the right here. And the third one will be the derivative of the Lagrangian with respect to lambda, or the Lagrange multiplier, is equal to 0. Okay, so when we do the Lagrangian method, we now have these three conditions for optimality. So I've taken the derivative with respect to our choice variables, C and L, and I've also taken it with respect to lambda, the Lagrange multiplier. Okay, and in each case, I'm taking that derivative and setting it equal to 0. So in our case, what are these? What are these conditions? So this first one just becomes, so the derivative of this with respect to C is, well, first this term. So the derivative of the first term with respect to C is the marginal utility of consumption, right? It's just the derivative of the utility function with respect to consumption. And then C also appears here in the constraint. So when I take the derivative of this second term with respect to C, what do I get? I would get negative lambda is equal to 0. Okay, and similarly for my second condition here, I would get the marginal utility of leisure. So I'm taking the derivative now with respect to L leisure. So the first term here, we have the marginal utility of leisure. And then leisure also appears in the constraint. So taking the derivative of this second term with respect to leisure would give us negative lambda, W is equal to 0. And then importantly, when we take the derivative with respect to lambda, the Lagrange multiplier, it just returns the constraint, the budget constraint. So notice that taking the derivative of this whole function with respect to lambda just returns all of this in the square brackets. And so all of that in the square brackets is just my constraint, right? We can rewrite this as C is equal to, by bringing C to the other side of the equation. And just to kind of preempt what's going to happen next, I'm also going to rewrite our two other conditions. So I'm going to take the lambda and put it by itself on the right-hand side. Okay, and so that gives us three conditions, which just for clarity, I'm going to write again on the right-hand side here. So our three conditions are: 1, the marginal utility of consumption is equal to lambda. 2, the marginal utility of leisure divided by the wage is equal to lambda. And 3, just our budget constraint. There we go. And those now become our three conditions for optimality. So notice that when we did this before in the heuristic way, in the intuitive way, we had two conditions for optimality. And now we have three, and we have this extra variable lambda. So it seems like we're not necessarily better off here. You know, we have 3 conditions instead of 2, and we have this extra variable. Well, on the next slide, I'll show you that by getting rid of that extra variable lambda, we just return the exact same conditions that we derived earlier. Okay, so I'll copy these over here. Watch this. I'll start writing in blue again. So combine, there we go, 1 and 2. So in other words, I'm just going to set 1 and 2 equal. Well, what does that give me? Marginal utility of consumption is equal to, I'm sorry that keeps happening, is equal to the marginal utility of leisure divided by the wage, or rearranging, marginal utility of consumption times the wage is equal to the marginal utility of leisure. And remember that this is just our same optimality condition as before. So that now, I'm going to call this 1 prime, combined with the budget constraint, which I'll call 2 prime, gives us the exact same conditions for optimality that we saw before. So this Lagrange approach yields us the same conditions for optimality. Okay, 1 prime and 2 prime are the same conditions we saw before. We've just arrived at them in a different way. And so again, what's the advantage of the Lagrangian? It's foolproof. It'll always give you the right answer as long as you set it up correctly. The intuitive method that I showed you, sometimes you have to think about it, right? In this Lagrangian, you're just plugging things in and solving. It gives you the right answer. In the intuitive method, you have to think about where these conditions are coming from. So if I change the problem, for example, you would have to think in the intuitive method, how does this change the intuition of balancing these 2 marginal utilities relative to their prices? In this one, you don't have to think about anything. You just plug it into the Lagrangian and you take what comes out and you solve. Okay, so that's the Lagrangian. I figured I'd show that to you guys. You'll have to know it eventually anyways. You'll likely see it later on in this course as well. So there you go.